polynomial equations, specifically the really high degree ones.
Exactly. If you've ever done algebra, you know polynomials can get, well, messy. But picture a 19th degree equation, all those x to the power of something terms.
A lot to handle.
And for ages, the standard thinking, thanks to the mathematician Niels Henrik Abel, was simple. For degree 5 or higher, no general symbolic solution exists, period.
Mhm.
So mathematicians had to rely on approximations. And you know what that means.
Headaches,
Huh.
rounding errors, instability.
Yeah.
And Abel's theorem back in 1824 was quite definitive. It set a real boundary.
Yeah.
It stated that exact solutions expressed in radicals,
Yeah.
using just the basic arithmetic plus roots.
Add, subtract, multiply, divide, nth roots, that sort of.
Precisely those.
Yeah.
For degree 5 or higher, those tools just weren't enough. It wasn't just hard, it was considered impossible.
Leading to centuries of essentially guesswork. Educated guesswork, maybe, but still.
Guesswork nonetheless. Never the true, precise answer. You always had that uncertainty.
But the sources we looked into today, they suggest a new door has swung open thanks to a completely new method introduced just recently in 2023 by Murad Sultan Izzuidi.
Izzuidi's theorem, yes.
And this theorem seems to do what everyone thought was impossible. It gives exact, symbolic, closed-form solutions.
For any degree polynomial.
Any degree. So our mission today is really to explore how this changes things, how it redefines polynomial solving. And we'll use that 19th degree polynomial as our test case.
Right. And it's important to see how this fits with Abel's work. Izzuidi's theorem doesn't actually contradict Abel. It sort of transcends it.
That's so.
Well, Abel focused on solutions and radicals, limiting the toolbox, as we said. Izzuidi's approach uses a richer symbolic language. The sources call them recursive power sums and deep recurrent structures.
Okay, that sounds more advanced.
Think of them as more flexible tools, much more powerful than just basic arithmetic and roots. They can capture the solution's true symbolic nature.
So it bypasses the limitations that radicals imposed.
Exactly. It allows for these solutions that were just considered unobtainable before.
So this gives a level of precision that classical numerical methods, even modern AI, they just can't match.
That seems to be the claim.
Wow. That really does sound like a fundamental shift. Okay, let's look at that specific polynomial the sources used. It really is a beast. A 19th degree equation. The coefficients alone are dizzying. We won't read the whole thing out, obviously, but just picture it. X 19th, X 18th, all the way down.
It's exactly the kind of problem that's historically been a complete nightmare.
Yeah, just looking at it makes my calculator want to hide. How would you even start on that traditionally?
Well, that's the point, isn't it? With traditional methods, you'd only get approximations. And for degree 19, the risk of those rounding errors piling up is huge.
You just can't guarantee an exact answer.
Never. Which is why we just accepted that exact solutions were impossible for problems like this.
Right. Okay, so let's unpack Izzuidi's theorem then. How does it actually solve this monster exactly? What's the core difference? What makes the impossible, well, possible now?
The key seems to be a very systematic recursive process. You start by putting the polynomial into a specific form. Then you apply these recursive relationships, these symbolic transformations, step by step, to derive the exact roots. It involves calculating a set of symbolic coefficients, the sources call them stay-at-r. And critically, every single one is found symbolically. No approximations creep in.
Okay, and as we dig into this method, the formula for these S coefficients, it looks complex on paper.
It does involve sums, binomial coefficients.
And it uses a specific coefficient from the original polynomial L0q, the sources call it.
That's right.
Which, for our big equation, turns out to be just 19.
Correct.
But the core idea, reading through it, is almost simple in concept. It's recursive, like building blocks. Each S term is built precisely from earlier S terms and bits of the original polynomial,
ensuring total accuracy at every step.
So it's like a chain reaction of exactness.
That's a good way to put it. The beauty is it doesn't guess. It constructs the solutions systematically. Each step uses the precision from the last one. So even after many steps, the exactness holds.
Okay.
For example, you apply the formula. For K0, the first step, you find Sarah's 1. Simple enough. For K1, S1R is 0.
0.
And what's really striking is that for many of the next K values, up to K7, and then again from K10 to K16, these scalar values, they all turn out to be 0.
Whoa, wait, a whole bunch of them are just 0?
A surprising number, yes.
That can't just be a coincidence, right? What does that pattern mean for simplifying this huge equation?
It's absolutely the key. This isn't random. Izzuidi's theorem, through this recursive process, seems to cleverly find and use some hidden structure in the polynomial. Because those specific scalar coefficients are zero, the method essentially collapses that massive 19th degree polynomial. It just simplifies dramatically.
Into what?
It shows that our original polynomial, px, can be factored and rewritten. It becomes x times a much simpler expression. By 18, say r by 9 plus s17r equals 0.
Hold on, a 19th degree mess becomes that.
That's the power of the method leveraging the polynomial structure via these coefficients. It reveals the underlying simplicity.
So if x times by 18, 8r by 9 plus s17r equals 0, then one root is obvious. X equals 0.
Immediately clear.
That feels like pulling a rabbit out of a hat after staring at the original equation.
It does, doesn't it?
Okay, what about the other part? The by 18's 8r by 9 plus s17r equals 0.
That simplifies even further, because if you look closely...
5 y 9.
Exactly. It's essentially a quadratic equation, but in terms of by 9, you substitute the calculated values for AR, which is 923,77199,
Okay.
and S17R, which is 923,751 plus 1918. Yes, there's a complex number in there. And then you can just solve for by 9 using the standard quadratic formula, just like solving A2 plus by plus C equals 0.
So if I'm following this whole recursive symbolic breakdown takes a 19th degree polynomial and boils it down to one root is 0 and the rest come from solving what's basically a quadratic.
In terms of by 9, yes. That's precisely it.
Why is that possible? What makes the simplification happen? It feels like the breakthrough part.
It is the breakthrough. It's because Zwidy's method doesn't just operate on the surface numbers. It digs into the algebraic structure. It finds relationships, like the fact that many coefficients were 0 that allow this factoring. It reveals the polynomial's true, simpler form.
And the roots you get from that quadratic part,
Yeah.
what do they look like? Still massive and complex?
They are complex numbers, yes. You solve for by 9 first, which involves square roots of complex numbers.
Yeah.
Then you take the 9th roots. The sources give the final form for the other 18 roots. It involves complex exponentials. It looks like x equals 1 plus 92377, 9277, 852, 9815, 125, 433i, 219, e 2 pi I m 9. Worm goes from 0 to 8 to give you all the 9th roots. But the crucial thing is,
It's exact.
it's the exact symbolic root. No decimals, no rounding. Expressed purely symbolically. And it all comes directly from those recursive steps, using that L0Q 19 value we mentioned earlier.
So what this means for anyone dealing with these, no more numerical approximations, no rounding errors.
Correct.
This isn't an estimate. It's the actual precise answer, even for degree 19.
Or higher.
That just feels like a completely different way of thinking about these problems. Are there limitations? What about computation time for even higher degrees? Do the sources mention that?
The sources emphasize its applicability to any degree, suggesting robustness. While computational complexity will naturally increase, the fundamental principle holds. Exact symbolic solutions are achievable. It truly makes the old reliance on numerical guesswork seem, well, obsolete for finding exact roots.
It outperforms classical methods, and you mentioned even AI system.
Yes, because AI often relies on numerical techniques or pattern matching, which can struggle with high complexity, instability, or lack of known general forms, like the radical solutions Abel ruled out. This method bypasses those issues.
It finds the exact roots for polynomials that we basically wrote off as unsolvable by exact means.
Precisely.
So for 200 years, we thought that door was shut tight on general symbolic solutions for high-degree polynomials. But Zwidy's theorem hasn't just nudged it open. It seems to have blown it off its hinges, offering exact, precise symbolic roots.
It certainly appears that way.
It really makes you think, doesn't it? What other mathematical problems that we've labeled impossible might actually be solvable if we just find a different symbolic language, a different set of tools to approach them with? Maybe rethink the very constraints we assumed were fundamental.
It definitely opens up possibilities, a new way of looking at things.